focuses mostly on electrification and energy efficiency. So that being said, Hydro-Quebec's procurement plan foresees a requirement for new energy by 2029, or actually by 2027. What this leads us to a pretty significant change in narrative, where Hydro-Quebec has talked about energy surplus for the last maybe 10 years or so, whereas now we're talking about new procurements. We're going to need more energy, and in the time it takes to develop, let's say, a new wind farm, 2027 is tomorrow morning. So we've had a call for tender that's ongoing right now that includes 300 megawatts of wind. Hydro-Quebec's strategic plan talks about a 3,000 megawatt wind energy portfolio. So why do we talk about wind energy so much? Well, if anyone looks at the wind or energy distribution of a wind farm in Quebec on a monthly average basis and overlay that with Quebec's energy demand on a monthly basis, there's a very strong link, or those two curves are very similar. So it's also been determined that when energy is competitive, you can deploy it quickly, closer to where the demand is. Quebec has a very particular situation where we need energy in the winter during peak loads. And wind energy has been demonstrated to be able to provide power during Quebec's peaks. I think it's along the lines of 36% of installed capacity. So we see wind energy in Quebec's energy mix in the future, improving on reliability and predictability in cold climate is very important, along with forecasting, grid integration, innovating on the regulatory side of things. So that there's a whole list of ways that we can innovate to increase let's say the penetration rate of variable energy in Quebec, and a lot of that is going to be wind energy. So that being said, I'm going to pass it on to Charles, who's going to maybe give a little word on the steering committee and then roll into his presentations.
Yes, thanks, Matt, for that intro. I think it's a great background. It's nice to see. I think that we're shifting the philosophy in Quebec that we've had for the few last years. So that's great news. Marianne, were you going to share the slides, or should I share my own?
I can, if that's easier for you, or you can if you have them.
Oh, I have them. I'll share them. All right. Just give me. Okay. So yes, I wanted to give a few words from the steering committee of the Canadian Wind Energy Research Network. Basically, the reason why we're here today, what's our motivation, what we hope everyone who's joining the session today will get out of it. And so the general idea of the network is to create a forum for collaboration. We want to gather researchers from across the country to talk about topics that they are focusing on or want to expand, and get new ideas and possibly some potential partnerships as well. And we want to accelerate the uptake and impact of research projects research products along the way. The membership in the network includes universities, independent research organization, industry, and government. And we're interested in all stages of wind energy research, whether it's fundamental or applied. And we hope that this collaboration will result in a higher level of innovation that is required to advance the wind energy industry in all the different contexts we have across the country. So we had an introduction from Matt about the Quebec situation, but going from the Atlantic to the West Coast to the north of Canada, there's a general need for innovation related to the integration of wind power. And cold climate is one of the challenges we have across the country. Our objective with the network is to hold at least one meeting per year. And although there's no funding attached to the network, we do hope that members that find common interest on a given topic can engage in joint research and pursue external funding opportunities. We don't, as the steering committee, kind of provide any funding, but we do we hope to see collaboration rise from those discussions. Members of the steering committee include Ryan Kilpatrick from NRCan, Rob Carivo at the University of Windsor, Lindsay Miller-Branovaki from the University of Windsor as well, Phil McKay at Kenria, myself, Charles from Mergica, Scott Harper, and Marianne, who's joining us today from WCAN. And this is today our second annual meeting. It's presented as a series of webinars, and we also have time for discussion at the end. We hope someday we'll be able to hold that in person. Hopefully those Zooms conference are reaching an end, or at least, we'll see. We'll come back to a more in-person event at some point. We have 5 different sessions this year. So we had this week wind turbine aerodynamics, grid integration, cold climate and forecasting is the one you're attending today. And then next week we have offshore wind, social and environmental integration. And then the last day is asset management next Wednesday. All sessions are recorded and they will be shared by the research network following this meeting. So yeah, that's the intro from the committee, and I'll switch to my other presentation because I guess I'm following up on the more cold climate related topic. So I wanted to present quickly two initiatives we have at Mergica related to cold climate. And so those are a project on the performance of icing detectors, which is reaching its end, and then also our involvement in IEA Task 19. So performance of icing detectors, the full title of the project is the Performance of Icing Detection Methods for the Evaluation of Cold Climate Impact on Wind Energy Production. It's a 3-year project, started in 2019 and just ended this year. Our methodology in the end was comparing data from 12 different icing detection methods over 3 winters to propose and evaluate field validation performance metrics. We have a research site based in Rivière-au-Nord, that's near Gaspé in Quebec, where we see here is a camera on the nacelle where we have MCMS ice detector. That's Patrice, I guess, we'll talk about it. We have an neologic sensor on that tube here, and we can also measure ice accretion with the cameras. We have several other ice detectors installed across the site. And yeah, the general idea was to get a sense of, are we able to compare those different sensors? Do they give similar outputs? And how can we compare them between each other? Because as some of you may know, some of them will detect instrumental icing, that is when there's ice accumulated on a surface. Some of them will detect meteorological icing. Those are when there's like active meteorological conditions causing ice accretion. and others detect rotor icing. That's ice specifically on the wind turbine blades. So we defined a set of variables, which I'm showing here. We have and those variables will always depend on if the detector, can detect that specific type of icing or not. So we split the analysis between the 3 types of icing. So some sensors, they're able to detect a couple of them, or all the 3 of them in some cases. Some only detect a specific type of icing. So those variables are adjusted. But basically, we've measured active ice accretion, the presence of ice, the ice accretion rate, the ice quantity, start and end time of icing events, the duration. Then we had also severity, which is the maximum accumulation of ice, intensity, the average ice accretion rate during an event, the availability, so the percentage of time we have valid data over the analysis period, and response time, which is kind of something we tried. It's been mostly used in a wind tunnel context, but we wanted to try it in a field context, trying to see the elapsed time between the actual start of the ice accretion, which we can determine from the image analysis, and then the active signal from the sensor. So what's the, let's say, lag between the 2? And the results and contribution to research we will give as an output from this project is a first comparison of long-term icing detection methods, availability and precision. If you look in the, let's say, public literature, there are some articles, like review articles, where you can find a description of those sensors, but you don't really find anything about performance on a very long-term basis. So we have a 3-year data set, and we can talk about the evolution of the metrics, interannual performance, and precision as well. So that's, I guess, maybe an outcome of this is that there's a variety of variety of ice detection methods, and it gives a wide range of results. So if you were to choose one sensor and do your site assessment out of it, you could have a very high uncertainty on the actual measurement you have on your site. So that's one conclusion coming out of this. We propose a new metric for in-field performance validation. That's the response time. And from that, we also had a kind of extensive data set of both meteorological, instrumental, and rotor icing. And for some of you who are familiar with the work of Task 19, there's something called the IEA ice class, which is basically a site category that you can give to a site based on the icing severity. And those categories are presented in terms of percentage of meteorological icing over a year, or instrumental icing, and then associated to a given ice loss or production loss from that turbine. What we found out is that the categories were not properly set for meteorological icing. So basically, if you were to use the metric of meteorological icing, you would end up over-evaluating the ice class you have on your site. And then up to now, there was no evaluation of what rotor icing could represent for those icing classes. So that's something we'll propose in there. We're working on the paper, so we hope to submit it in the next few weeks, and publication expected next fall or winter. This work has been supported by the FRQNT, and if you want more info, there's a link in there where you can have information on the project on our webpage, which kind of gives a background of my other involvement at Energica, the IEA Wind Task 19. That's the wind energy in cold climate. The IEA Wind Task are collaborative groups similar to what we're doing today, with this group here in Canada, but at the international level. focusing on specific topics. Task 19 has been running for quite a while now. It's been active since the early 2000s, and it focuses on wind energy and cold climate, and its mission is to improve the large-scale deployment of cold climate wind power in a safe and economically feasible manner. There's a website there. I invite you to visit it. There's a lot of great publications on best practices, available technologies, guidelines related to ice detection or performance of ice protection systems. So quite a lot of resources available through that group. The group focuses on a variety of topics. So as Matt explained in the intro, like cold climate itself has an impact basically throughout the project life of a wind farm. So it goes into project development, operation and maintenance, health and safety, standardization, and recent research. We have 10 participating countries now, mostly from Europe. Our new member is Japan, so that's a new addition we welcome in the group. They've been the group that joined from Japan. They've developed a small wind turbine adapted for cold climate conditions, and there may be a potential for its integration in our northern communities here in Canada. So that's to be followed up on. I'm the representative from Canada on that group. It's supported by Natural Resources Canada, but if you have interest in the activities of the group or have questions about our deliverables, our resources, if you have, I'll show what we're working on in the new work plan. If anything that I'm presenting kind of gives you an idea or something you'd want to present to the group, just feel free to contact me, and I'd be glad to share this with the Task 19 group. And so about our new work plan, we have 6 main topics. First one being uncertainty quantification. So Task 19 has been working a lot so far in providing tools for pre-construction assessment or icing loss. We feel those have matured enough, and now it's time to assess the uncertainty of those methods. And so there's a lot of market development in cold climate, and as there's a market growth in that sector of the wind energy field, well, there's also a need from insurance company, banks, and entities financing those projects to understand the uncertainty around the pre-construction assessment, but also in operation. There's the control of cold climate wind turbine, where we'll look into the ice protection system performance envelope, where we're involved in this group with Patrice and André from Université Laval. Patrice and André have done extensive work on this over the last few years, so that's great. I think that it's been acknowledged by the Task 19, and it's now something that the group wants to focus on. So congratulations, Patrice and André, on that. That's great work you've done. There's control strategies for cold climate wind. In our Canadian context, we want to get the most production out of turbines during icing events. And some operators here, they suffer a lot from, let's say, design assumptions that are made on some wind turbines that are shutting down turbines in some icing conditions. Principal reason being to protect the structural integrity of the turbine, and we feel that there's an improvement to be made in that field. So that's something I'll be leading over the next 3 years. There's safety and acceptance, where we want to look at the ICE-THRO tool. So DTU, the Technical University in Denmark, they've developed an open source code to do ICE-THRO risk assessment, and they will package it basically and make it available as an open source tool. There's distributed wind and icing. So this is something we'll look into with Japan and also with the people from Task 41, which is on distributed wind. And then there's the icing impact on wind turbine noise, which is also a concern that was raised for turbines that are closer to
Charles, I'm a little concerned with the time we have left.
Yeah.
If you can wrap it up, please.
Yes, sure. Last three topics are modeling and testing, market and energy system level impact, and then future proofing of cold climate wind references, which are basically transitioning from those like PDF reports that we have to a more open access, maybe a wiki type of page where the content would be updated on a more frequent basis. And apologies for the time here, but that's what I have.
No problem, Charles. Thanks. And there's actually a couple of really good questions. I would suggest, Charles, maybe you can answer them in the chat, or we can come back around to them during question period towards the end. But we have a couple more presentations to go through. So we could pass on to Marc Defossé, also from Nergica, who's going to give us a little update on Task 32.
Yes, thank you. I'll share my screen.
It's great to see some old colleagues, by the way.
Yeah. Hi, Matthew. So can you see my screen?
Yes.
Yeah, okay. Oops. Okay. So my name, hi everyone, first of all. My name is Marc Defossé. I'm a lead project manager, research and innovation at Nergica. And I will first give you a brief history of the task 32, which actually ended in 2021. So I'm working in the group Wind LiDAR in Cold Climate. The task started, the phase one of the task 32 started in 2011. There were 3 phases, and it ended in December 2021. Since there's still a great interest for the applications of LiDARs in the wind industry, it has been decided to relaunch the task 32 as the new task 52. So the wind LiDAR in Cold Climate group will be integrated in one of the themes of the new task 52, which is called large-scale deployment of wind LiDAR. Okay. So what was the wind LiDAR in Cold Climate group? It was composed of 3 subgroups: operational, science, and deployment. Each subgroup had a leader, which was responsible to ensure that the work was progressing in his subgroup. And we held regular 5-week meetings between all the 3 groups to share the results and discuss topics of interest. I now present some of the work we did at Nergica. And the first part is about data availability against various meteorological parameters, like here in these figures: air temperature, relative humidity, atmospheric pressure, or cloud height. The purpose of this is to do a sensitivity study in order to determine which parameter is more important for the data availability. The data that you can see on those figures were recorded in 2015, but we are continuously collecting the new data. We are also trying to see if the LiDAR data can be used to detect icing. So you can see on this figure a comparison between the CNR of the data and the ice detected with the meteorological ice detection. And we are trying to develop methods to understand how the icing can be detected with LiDARs, and this is still a work in progress, actually. We have also installed 3D LiDAR at our research site. The point of doing this is that we can measure the aerosol density just around the turbine, as you can see on this figure. Not that a sweep like this one on this figure can take a few tenths of seconds. So it's possible that in the future we will have to reduce the angle of sweeping because we have to make the assumption that during a few seconds, the meteorological conditions do not change too much in order to have relevant results. So the LiDAR is installed actually at our research site at Riviera Rona. We had a few troubles with at the beginning, so we don't have a complete set of data, but next winter we hope that we will be able to do more in-depth analysis. So thank you. That's it. Thank you.
Thank you very much, Marc. And I guess let's just continue on with the different presentations and keep your questions for the end. And if you have any in the chat that any of the presenters, feel free to answer along the way. So next up would be Fahed Martini from Université du Québec à Rimouski.
Hi everybody. Maybe I need to share my screen. Okay, thank you. Okay. So what I'm going to present today is derived from my thesis on modeling and simulation of aerodynamic losses due to wind turbine icing. The long-term objective is to develop an intelligent system that can in real time predict icing and assess its ability in order to optimize the wind turbine operation under icing conditions. The main impact of icing is the aerodynamic drop due to airfoil deformation. So this will bring the turbine to lose much of their productivity. The solution, as Charles explained, that it is ice protection systems, and in order to use the icing protection system, we have to use a reliable icing detection system. I saw what Charles presented about the development of ice detection system, but in case there is drawbacks of these systems, this subject will be an alternative solution for predicting ice. So what I propose is an intelligent system that have correlations between weather conditions and the power loss, and it can be used in real time. Instead of analyzing every time the iced airfoils by costly CFD simulations, though this solution proposed to make use of Arbit estimation of dynamic losses that I inspired it from a study in VTT in Finland. So the use of McConaughey model that is analytical predict ice on the cylinder on a cylinder. At the same time, using CFD simulations at the same weather conditions for several weather conditions, in order to conclude or to deduce a conversion factor, and that is averaged for a range of scenarios. After predicting or averaging this factor, we will make use of an representative case in which we calculate the aerodynamic drop and use this representative case in, as a base of our analytical calculations for a lot of scenarios. It uses these two equations that are based on the ratio of mass of ice between the cylinder and the airfoil. I choose to limit my study on Rime ice, so between -5 and -10 degrees, and I prepared a database between weather conditions, icing weather conditions, and the percentage of aerodynamic loss for every case. So this database has been analyzed using neural networks using the neural networks, of course, in case that everything is well done, that will lead to a correlation between icing conditions and aerodynamic drop. Realizing this project, maybe at a long term, can be used in its finality as an indirect ice detection system and decisions to support the tool for wind farm operators, allowing them to decide on the most suitable scenario of operating according to the icing condition observed. Thank you.
Thank you very much. Very interesting.
Thank you.
Good work on the simulation side that could would likely be very interesting to compare with some field data eventually. Thank you very much. I think the next presenter up would be Andrea Kraj from the University of Saskatchewan.
Hi, everyone. Yeah, it's me. I'm over here. Yeah, so thanks for having me. My name's Andrea Cry. I'm at USask right now, and I am going to speak on climate change impacts on energy transitions in the Arctic related to wind. So as we prepare to deploy into the Arctic, and a lot of this work has been related to my work as a Fulbright Arctic scholar the last year, we face many new and daunting challenges for infrastructure and energy development in this area. And so we're looking at topics related to sustainable development goals specifically to the Arctic that are unique. We're looking at the changing Arctic environment, the built environment, wind turbines in the area, as well as community power needs and Arctic energy, of course, in these cold climates. So I'm just going to see if my screen is changing. It's a little bit slow. Okay, so the Arctic is often considered ground zero for climate change because Arctic air temperatures are rising approximately twice the rate compared to the rest of the globe. So, however, the diverse facets of Arctic climate change affect the built environment to a greater extent than one might assume based on warming air temperatures alone. There's many different impacts, but I'm just going to speak to the decreased foundational integrity of the terrestrial infrastructure in this case as it relates to wind turbines. So as you can see here, this is an image of the circumpolar north. It is from the Nunatak project, which aims to study permafrost distributions and trends and how its melting could impact climate change in indigenous communities around the Arctic. And this map is from 2019, and it's used to visualize terrestrial and submarine permafrost in the northern hemisphere. A lot of people don't realize that there is submarine permafrost. And so what is permafrost? Permafrost is technically ground that remains below freezing for a continuous period of at least 2 years. And as it melts, it releases methane, potential greenhouse gases, and of course, microbial decomposition. And this release of the methane contributes to global warming and continues this vicious cycle of permafrost melt, forming this feedback. So what's happening is that this thawing of the ice-rich permafrost threatens the integrity of polar and high altitude infrastructure. It is thought that 30 to 50% of critical circumpolar infrastructure will be at risk by 2050. That means 80% of buildings in Russian cities, 30% in Tibet of roads, and 70% of current infrastructure in areas that will have a high potential for thaw by 2050. This is going to exacerbate costs beyond 10 billion US by 2050. And right now there are mitigation techniques being developed for preserving and cooling permafrost and stabilizing the infrastructure. And why is this important? Because Arctic energy security is one of the most largest threats to the remote communities in this area, who are facing not only impact on their livelihoods, their quality of life, but right down to like vital situations of medical needs, hospitals, and the preservation of food and sustenance. So we're seeing issues around community displacement, the high costs of electricity, which are going to lead to profound economic disruption, and of course, the unreliability of these systems in these remote areas that are not connected to the grid. This threatens the quality of life and of course, leads to ecological disturbances. Populations remain vulnerable and under the control of the foreign interests related to fossil fuels, because many of these communities rely on diesel and other fossil fuels for their power. And the unique part of this in cold regions is the impact of the warming climate on permafrost. So what does this look like? The circumpolar infrastructure risk by 2050 is depicted here in blue to show what is expected to exist in 2050, and then the thawed permafrost. In the red, we see the risk to infrastructure highlighted in high, medium, and low. And so you can see there's a great area of Canada that will be disrupted with this impact. Now, what does this look like on the ground? We see thermokarsts happening. There are where the ground sinks in and then a lake forms. We have the roads caving in, buildings cracking, and of course, critical infrastructure such as bridges and connection points that are falling apart. And this visualization of the infrastructure shows just how impacted the ground is. And it directly impacts the ability to build new infrastructure, meaning wind turbines and other infrastructure for energy. It's an exponential threat. And not only will the new infrastructure be needed, but if the roads don't function to enable the transportation and accessibility to communities to get to good sites, then it can't be built. So new methods are needed to build in uncertain terrain and conditions that are constantly changing. And I characterize this as we need a new building code for category 5 climate change rather than say hurricanes and hot climates, which is another area I've worked in for many years. And I've already mentioned the thermokarst example, which is, I'll just highlight here in E in case you're unfamiliar with that. Okay, moving on. So what does this look like in terms of remote communities? So there are many remote communities located in areas of discontinuous, sporadic, and isolated permafrost. Again, we're looking at this from the circumpolar view. And the polar regions here are the ones that are warming 3 times faster in some areas than the global average at 3.29 degrees Celsius warmer than the period between 1981 and 2010. And so we can see here how many are impacted. And according to the authors of this report, there are approximately 5 million people that live on permafrost as of 2017. That number could be down to 1.7 million by 2050, just because of the drop of the movement and the thawing of permafrost, and not because of population loss. So what does this look like? Let's zoom in a little closer. So the 2060 scenario, and this is a visualization of a map from 2060. I've been talking a lot about 2050, but this goes as far as to 2060. That can mean a loss of 3.25 million people impacted by this thawing permafrost regions. So what we need to do is raise awareness and spur communities to plan for this change. And so there are about 1,162 settlements that will be impacted, but because there will be only about 628 that remain at 2050. So it's quite large in scale. And so this risk is facing the community. It largely depends on the geology, because in some areas, the soils are 90% ice. And if we lose that, that would mean a 90% loss of volume. So In terms of wind, what do we see here? From the Arctic Renewable Energy Atlas, we see annual average wind speeds here shown around the land masses that I've collected here. The bright yellow, I've also plotted global horizontal irradiance, because in the summer months, the Arctic does get nice sunsets and sun days. But what we can't rely on that in winter, right? So we need to have a diversification of our resources in these regions. Now, the Arctic Circle here is plotted by the purple circle, and it is defined at a latitude of around the Earth at 66 degrees and 30 minutes north. So you can see we have some good wind resource in this region. In terms of wind density, at 100 meters versus 200 meters, we also have some good resources. But what does that actually translate to? Because the question becomes, can we support the size and scale of infrastructure in the Arctic given the changing environment and uncertainty and instability? And what we see in a lot of Arctic wind turbines that are implemented, we see small scale ones. We're looking back to like 37-meter height, hub height. So I've highlighted that here in red, because this is, I'm going to show you an example right away of what happened by a 37-meter hub height wind turbine. The question is, can we even get to where we're going in the potential of this? And the question will be, can we do onshore, or will we have to rely on offshore? And what is the impact when we start having submarine permafrost as well? Because this is a completely new terrain that we need to manage. So let's take a look again at this map. I've turned it slightly now, and we're going to look at opportunities, barriers, and mitigation around the reality of community energy in these cold climates. And so we see here our communities in Canada, as well as some of our neighbors. Now, I've plotted here a close-up of the remote communities that rely on fossil fuels diesel primarily in Canada. You can see we have a lot. These are the ones that are located in the continuous permafrost zones, discontinuous, and the sporadic and isolated zones. We're going to have a lot of communities impacted by this, and they already are. We're seeing this already. So the opportunity here is that we have the chance to revitalize rural and remote communities, especially a renaissance for Indigenous communities as a way to reconnect with the land and build new ways for energy autonomy and resiliency. But this is also a warning. We can't simply implant technology without community buy-in, because renewables won't work this way. There are ways to mitigate technologies for the built infrastructure in Arctic permafrost by using examples of what we see in buildings in other ways. However, we have to pay certain attention to how this will change when we impose wind turbines and other such technology. Now, let's look at this for a moment here. In unheated structures, like such as roads, airports, railways, etc., sometimes they can be located in permafrost areas with minimal consideration for protection of permafrost from thaw. This, of course, will be changing as the permafrost retracts. In discontinuous permafrost zones, conditions are generally warmer and more advanced mitigation techniques may be required. So we're looking at things like roads, rail embankments that can cause permafrost thaw simply through the surface disturbances that remove the native vegetation and warmer surface temperatures. What we have here in figure 4D in the corner are ways that thermosiphons have been placed in the road to help to passively cool the land that these buildings are on. We're going to get into the next picture here, which shows what has happened with a wind turbine. Now, this is the example of—
Can you wrap it up in about a minute, Andrea? Is that—
Yeah, well, I got pushed back by others. This is so good. Everybody needs to—
Yeah, it is. It's excellent.
So this is a 100 kilowatt wind turbine generator at about 37-meter hub height. So what happened with this is that we see evidence of permafrost degradation around the turbine. We have thermal karsts happening in the lake beside it. We have soil cracking. And if we start to compound the issues, including severe icing conditions, which add uncertainty to these dynamic properties, we can be in a situation that will lead to potential immediate structural damage or long-term fatigue-induced structural failure. We know that the freeze-thaw cycle compounds this to order of two orders of magnitude. So thermosiphons are important, but in order for them to work, the air temperature must be cooler than the surrounding soil temperature. So if we have issues with rising temperatures in the Arctic, we have to start looking at new ways to even support our renewable energy and targets in there. So I'll go through this quickly. We know that the cost for renewable and diesel power and electricity in remote communities is exasperated. We've seen this in the remote communities in Manitoba. In the diesel zone, the prices could go upwards of $2.36 when surcharges are added from the baseline. So across Canada, we also have these issues where we need to move to having more renewable, affordable, sustainable, and reliable renewable energy systems, especially in our northern remote communities. And the way that my work has shown that this is possible is that when we combine distributed generation in an intelligent way with intelligent control through a balanced microgrid that works together, we can also save money. But the big component in the Arctic will be the wind factor, as well as building, because we cannot just rely on solar and of course batteries backup and so on and so forth. So what will that wind play? And while we zoom back out on this, we need to also consider the impact of greenhouse gases and emissions that can be mitigated by just the increase of adding a 20% renewable energy ratio in our supply chain. So high stakes, we need to start changing that from a macro level, as well as our very siloed icing world that we deal in with wind energy. And so some closing thoughts around this is that, yes, the pursuit of technological advances should continue as engineers seek to design the infrastructure on an increasingly unstable landscape. We need stable infrastructure. The reality is that offshore wind might be the more stable long-term pathway for Arctic wind development in some areas, especially for the coastal communities. The inland communities where we need onshore wind development will be limited to accessibility of the site, the stability of the land, as well as the mitigation of permafrost thaw at that added cost. And the cost, the mitigation of the permafrost issues and the uncertainty of building in this unstable climate will impact the levelized cost of electricity of wind development. But at what cost comparatively to that of remote energy is to be determined. And thank you for your attention. You can reach me here. This is my email and my website. Thanks.
Thank you, Andrea. Very interesting. I think next up would be Patrice. In terms of time, we're running. We've kind of, I guess there was probably a break planned, which we're probably going to lose, and we're running into the forecasting session already. I think there's someone from the forecasting session who won't be attending, so we've gained a bit of time there. But anyways, Patrice, if you can state your name and we can pass on to the next person.
Yeah.
I'm just kidding. No, I'll give you a, you got your 5 minutes.
Yeah, thank you, Matthew. Do you see my screen well, or do you hear me well?
Yeah.
I'll
Yes,
try
we
to
do.
stick to my 5 minutes and go very quickly. So my name is Patrice Faberge. I'm a PG student at Université Laval, and I'm going to present on new tools to evaluate the performance of wind turbines under icing conditions. So Canada is known for its harsh icing conditions. So this is also the case for icing. And as you can see on the figure on the right, there's a lot of wind farms installed in places where the icing frequency is high. But fortunately for us, there's a lot of solutions for the challenges associated with icing conditions. But the question is how to assess the solutions for wind energy in cold climate. What do I mean by solution? I mean alternative operational strategies, or AOS. So AOS can include ice protection systems, control strategies, or coatings. And they also include everything from the installation of a new solution, the modification of an existing one, or the modification of an activation strategy of an existing solution. So before we get to evaluate the performance of the AOS, we need to prepare the data. This is often, this is the most important part of the process, and it's often overlooked. If it's not done well, it will lead to false results. The challenge here is to work with imperfect data. And sometimes we have like false status codes and holes in the data. So we need to do a good job to have good results in the end. So in the bottom of this slide, we can see two power curve scatters. So the one on the left is a typical unfiltered scatter. So and the one on the right is a filtered power curve scatter. So how do we get from the one on the left to the one on the right? We can identify maintenance and stoppage events, and we also need to identify icing events. And we cannot just shave the top and the bottom part of the power curve. We need to identify those periods, knowing that they not only influence one turbine at one timestamp, they happen in a certain way in regards to time, and they also influence the other turbines near. So once we have a clean power curve like the one on the right, we can build a power curve model that will help us to estimate the available energy and then the energy losses. So how do we evaluate the performance of AOS? We use a concept based on the scientific method. So we will have two groups, one experimental group where the turbines will be equipped with the AOS, and one control group where the turbines won't be equipped with the AOS. So in that way, we will be able to isolate the effect of the AOS on the turbine production. But the thing that we need to make sure that's okay here is to have two similar groups, because otherwise we will have some biases in the results. So here's an example of a case study where we have an experimental turbine with a retrofit hot air IPS compared to 3 control turbines without the AOS and over a 15-day event. And we can clearly see that the experimental turbine produced significantly more energy than the 3 control turbines. And if we add the available energy, we can truly grasp how the turbine performed during this 15-day event. But how can we get from this visual outlook to numbers? We will need to use metrics. So usually we use the energy production difference, the energy loss difference, and the energy efficiency difference. Unfortunately, those metrics are sensitive to the selection of the period on which we decide to compute them, and in the difference in winds between the two groups that we have. So that's why we introduced 2 new metrics, the energy gain and the potential recovery, to lower the impact of these 2 factors. So I've gone really quick in my presentation. I haven't had the time to present everything, but the full methodology is presented in a 2-part paper that is referenced in the bottom right of this slide. What I want you to remember from this presentation is that cold climate solutions are available and more field testing is needed. And every site is different, but the methodology does not need to be. So thank you for everyone. I hope I haven't taken too much time. And if you have any questions, ask me at the end.
I was muted. Thank you very much, Patrice. That's great. Very interesting to see these methodologies evolve, and definitely some interest, I think, in standardizing them. Without further ado, I'm going to pass on to my colleague Lu Chen, who's going to moderate the forecasting session. And then hopefully we'll still have a bit of time towards the end for some discussion. And those who want to stick around a bit longer, more than welcome to.
Thank you, Matthew. I think we'll continue with the presentations for wind forecast. We'll skip the break, and then we will allow more time for the discussions at the end of the presentation. My name is Liu Chen Chan. I'm with the University of New Brunswick in Fredericton. I'm a professor emeritus at the university, meaning retired. I have been working with our colleagues on wind energy. I believe we started in 1994. The first project was with WECAN. At that time, it was called Atlantic Wind Test Site, but mostly on the wind inverters and grid integration side. Introducing the topics of wind forecast, we all know that wind operators and utilities would need to know the wind production in short time. For utilities, particularly for utilities, it's important to balance the generation and the loads as wind is highly variable, we need other resources to balance the generation and the loads. As a result, accurate short-term wind forecast is very important. For wind farm operators, not only that we need to know the energy production to bid into the electricity market, we also need to have wind forecast to plan for maintenance and shutdown, particularly under the severe ramp events. With that, we do have in Canada lots of activities on wind forecast. I will introduce two presentations. Unfortunately, we missed the one of the three planned for the presentation, so we will have only two presentations for wind forecast. I will ask each one of the presenters to try to present in a few minutes, so we will free more time for the discussions on both icing and forecast. With that, I will ask Dr. Bo Cao from University of New Brunswick, who is a research associate at the university. All yours. I don't know whether you want to present from your computer or
sure.
Marianne.
Sure, thanks, Dr. Yeah, thank you very much. So I try to share my screen. I believe so. Can you see my screen? I see my screen. Hello.
Yeah.
Hello, can you hear me?
Yeah. Well.
Yeah. Okay. Thank you, Dr. Chang. So yeah, so just my name is Bo Cao. I'm from the University of New Brunswick. Just like Dr. Chang introduced, in the past few years, our groups have collaborations with R10 to provide some investigations on short-term wind power production forecasting. But today, I may present something new, so some our recent interest on the wind forecasting technologies based on limited historic data. We know most wind forecasting methods existing in recent research and industrial applications require other details, physical descriptions, or more popular, a considerable amount of historical data using data analysis approach to provide the very effective wind forecasting, particularly wind power production forecasting. But there is a question. So if one we would like to provide a forecasting service for new wind farms or the wind farms after upgrade, like more wind turbines added, or if we would like to make a planning, wind farms planning, so even the microgrid planning, so how many turbines we need. In that, in those cases, how we could provide forecasting services. If you look at these pictures, this is the middle line is come from the manufacturers. It's we call this manufacturers power curves. Now it's for new wind farms. We all depends on these manufacturers curves to estimate the wind power productions. But actually, it's one we did. This we use 3 years data to verify the curves. We found that there's a much difference. So based on these situations, how we could provide our wind forecasting services. Here is some ideas, because in our previous project that we have we collect a huge amount of data from a few wind farms across Canada. So we have the data or historical data for a few wind farms. How we can use that data? So in this case, we introduce transfer learning techniques. So that means like, okay, if we already have the wind farms from the wind farms with a lot of historical data, we have the models for very accurate forecasting models for data investigated wind farms. Can we learn something from the existing wind farms, the existing models, and use that models for any new wind farms? That's the basic ideas. So when we look into the layout of the wind farms, we find typically the wind farms layout, we can have the line shape, grid shape, line shapes like the Alberta's one. The grid, like there's wind farms. I give examples in China, and the groups like the everyone's familiar with that, the PI. So can we, when we thinking particular is the one the wind farms have a very similar layout, can we learn from the existing with the wind farms with quite a lot of historical data, so with existing models? So in this case, we design a new method or a more general generic method. It's just like we divide the whole wind farms with 4 directions: north, south, west, and east. So we figure out the each directions what is the maximum power rating of these turbines can generate, and then we input each direction's power nominal power into our deep neural network. And we also collect the data from the Environment Canada's models using their day-ahead wind speed forecast, using their wind direction forecast, and also collect the telemetry data from the wind farm. So based on that, we will develop a network for, if we have a historic data, we can training this network, and this networks, this knowledge can be used for any new wind farm with a similar layout. That's the basic ideas. So we did some result, did some preliminary result, and we found we used very general metrics to evaluate the performance. This purple one is the new wind farms, just based on the power curve, manufacturer power curves. We will see these the MAE would attend like more than 25%, even the RMSE even higher. This blue line is the used directly. We don't have any historic data. We just use the models learned from another wind farms with very similar layout, and they can reduce improve the accuracies by 15%. 15%. And this green ones is using the existing models, but combined with 3 months historical data. The yellow one is that we just when we have 1 year's historic data, so how we could get the performance, the forecasting result. We will see that if we have historic data for existing wind farms, and we know they may have the layout similar layout for a new one, we can use these transfer learning techniques to provide more accurate forecast for a new wind farm. Yeah, that's my thank you. I just try to give us some new ideas that to see if this service is necessary.
Thank you, Bo. We do have probably time for one question or so. If anybody has a question, you may unmute yourself or type the question on the chat box. Seeing none, probably I will. If both you can stop sharing,
Sure.
I will ask Simon Philip or Franco from Environment Canada. Lots of work have been done at Environment Canada. I believe Simon Philip, you are going to
Yeah.
present, right?
Yes, exactly. Can you see
Go
my
ahead.
screen?
Yeah, it's getting there. If you can put
There you go.
it on. Yeah, that's it.
And then maybe I can put this like this. I don't know how to remove this thing.
This is good. This is good. You can go ahead.
Well, okay. Thanks, Lucien, for the introduction. So I will be presenting work I've been doing with Franco Petrucci on icing and wind forecast for wind energy. And we are both working at the MSC. The MSC is the Meteorological Service of Canada. It's a Canadian scientific agency that provides Canadians with accurate information on weather, warns Canadians about high impact weather, provides data and services to support provinces and territories in many areas, and supports federal departments in delivering their mandates. You can see how the MSC spread across Canada. There are many different offices. Our offices are located in Dorval. It's the Canadian Meteorological Center, the CMC. This project I will be telling you about today is financed by Natural Resources Canada since 2016. It has as a goal to provide high quality supercomputer numerical meteorological forecasts to the scientific community that performs R&D to optimize the integration of wind energy in the electrical networks. We have two main external collaborators on this project, namely Energica for the icing part and the University of New Brunswick for the wind forecast part. Let's start with icing. So icing and wind turbines, as you know, has been a subject of some discussions. It can lead to various problems, for example, larger fatigue loads, ice throw, or decreases in production. This can come from, for example, modified blade aerodynamics or being forced to shut down the turbines when there's too much icing. This can imply several $1 million in losses for the industry. Our goal here is then to provide improvements in the forecast of icing and of related production losses. So in order to improve the icing forecast, we have developed what we call an icing suite that allows us to provide our collaborators with more detailed data than would be available publicly from the model outputs that are available from the CMC. The suite is based on the outputs from the HRDPS, which is the high resolution. Excuse me, maybe I can I just remove this? No, no, okay. It's a bit annoying, but okay, it's okay. So from the HRDPS, then the high resolution deterministic prediction system, which is run at the CMC 4 times a day with a lead time of 48 hours. And the suite has 2 parts. It has a part that provides data at lat-long stations corresponding to wind farm locations, and also on a grid located in the eastern part of Canada, as shown here. So what we do is that we apply an icing algorithm based on the work in this paper here that for which I give the reference. And this icing algorithm, it's a bit similar to what has been discussed before. It predicts an ice acclimation on the cylinder, and then we do that internally, and we also send the data from the HRDPS that we treat with this suit to our external collaborator, Energica, that also applies this algorithm, but a revised version of it that they've been working to improve. They also perform energy loss calculation, so going from the ice acclimation to an energy loss calculation, and they also perform some verifications. And in our case, we have been lately putting data available on the WMS server in an experimental mode so that it's accessible to the public. And I will show you what kind of results you can get from there. So WMS, first of all, it stands for Web Map Service, which is a standard protocol for providing geo-referenced map images over the internet. And the data on this server can be accessed using, for example, this interface here called MeteoSound Plus. So you can go there and have access to the different fields that are available. You can do maps, visualize the data. So for example, I show screen capture here of icing in milliliters millimeters per hour for a certain forecast day last week in March. You can see that you had a lot of icing forecast to occur in this zone here near Gaspé and the Gaspé Peninsula. And then this is the type of result that you can visualize on this interface. But knowing what fields are available, you can go further and you can use scripts, for example, written in Python to access the data with more flexibility. And I will show you what kind of results you can get. So here, what I show is a net accretion rate in meters per second for a certain forecast day last year. It's shown here as a video that is made up by superimposing different maps, which are made every half hour for about 18 hours. And you can see in this case that you have an important icing system that is forecast to travel in this zone. So I think there's a lot of interesting things that you can do with such data. And within a couple of months, we aim at providing some scripts that can be used for the public. And the people that use them can adapt them to their own needs. So more generally, that what we can get from our icing suite, I wanted to show you also a platform that you can use to get access to the operational model outputs at the SMC. Sorry, this platform is called GeoMet. So it's a platform that provides public access to the MSC data via application programming interfaces, API, as shown here. So you can see a screen capture of the home page of GeoMet. So the same mechanics can be used as for the WMS server I showed you to look at the data and to access it. But the difference is that GeoMet is a platform. You can get data from operational model outputs, while the WMS server can host experimental products. And Python can also be used in this case to access data in a very versatile way. So using scripts, you can get the access to the data you want at the time step you want for the grid point you want over a grid and so on. So it's very versatile. So for example, what I showed here is that what I get as a map. So I asked Python to output a map of the temperature, for example, in this area. And this is what I got here. So I got the 2-meter temperature forecast from the HRDPS extracted on a subgrid at a certain time step of a given forecast. So I could do it using a script in a very powerful way without having to download files and then get the data from the files and treat the files and so on. So it's very powerful and easy to use. Now let's move to the wind part of the project. So we've been working mostly on forecasting power ramps, and power ramps are defined as large and sudden changes in wind energy production, either going up or down, and they result from changes in the wind resource. And they are difficult to predict, and therefore they are a challenge for the industry, as down ramps can force network operators to use other sources of production to compensate for the losses due to ramps, while up ramps force network operators to have to offload energy, so wasting this energy in order to avoid overloading the network. Our goal here is to improve the wind and the power ramp forecasts. In order to do so, one thing we've been doing is that we've been running GEM ourselves on a smaller grid 4 times a day. On this grid here, centered around the Maritimes and the Gaspé Peninsula, with the same resolution as the HRDPS. I should mention first that the GEM forecast is the model. A GEM model is the one that is used at the SMC for operational for running numerical weather predictions. We use the same resolution, but we run it to have mostly control over the outputs of the model. For example, in this case, we ask the model to output data every 3 minutes. And note that the time resolution for the data available to the public is 1 hour, so it's quite different. And within this project, we interpolate the data at wind park locations and different heights, and we send it to the University of New Brunswick. And on their side, they work on identifying and forecasting the power ramp, so going from the wind forecast to power forecast. They work on developing an interface for the industry, and they also perform some verification work. And I was telling you about a higher time resolution here. The use of a higher time resolution was for the output was defined as a low-hanging fruit for improving wind energy forecast by the International Energy Agency WERN program. It indeed allows to better predict the onset and the end of ramps. And I'll show you in this figure here how this comes into play. So you have here a forecast of the wind as a function of time at a specific location here corresponding to Energica's experimental site for a day last year. And I simply compare here the resolution output of 30 minutes in red with the resolution output of 3 minutes in blue. So you see in a very clear way here that if you use a 30-minute resolution output, you would miss the peak and the through of the ramp, and you would also miss the sharpness of this event here. And even more so, it would be even worse if you had a 1 hour output. So you can see in this very simple example how useful it is to have a higher time resolution for the outputs. And now I wanted to show you as well, before I showed you how I extracted a map of the temperature, and I also just wanted to show you quickly how you can extract a time series, for example, of the wind velocity. So what I did is I used a Python script and I asked to output a time series at a given, for a given forecast at the same point at Energica's experimental site. And then this is what I got using the script. So I show here the wind velocity in knots as a function of forecast time, so for the 48 hours of the forecast. So in a very powerful way, I could get this forecast without having to download any file, but just by asking the database. And going back to our own work here, what we're doing to improve the wind forecast is that we've been going further than 2.5 kilometer runs, but we've been running GEM forecasts using a 250 meter resolution on a small grid on this site here, which is a very challenging site at the northern tip of PEI. In order to do this, we go from a cascade, we do a cascade in the calculation going from the HRDPS forecast to a 1 kilometer forecast and then to a 250 meter forecast. And this, as I said, is a challenging site here, and we believe that a better resolution should allow us to better represent the flow around this complex site. I show here an example that illustrates the kind of difference we get in the detail of information with these two forecasts. So we have the forecast 2.5 kilometer resolution on the left and the 250 meter one on the right. We compare the wind velocity in knots in these two cases for a run in May last year. So you can see that you get quite many more details on at the right. And we believe that the representation of the topography of its effects are better in this case, but we need more verification to be able to quantify the improvement better. And in order to improve the forecast, we are also looking at other ways. So lastly, I'll tell you about a Kalman filter that we've been working on to improve the forecast. So we see here the specific location at which it was applied. So the same location as the one used for the higher resolution forecasts. And in order to apply the Kalman filter, we need observation data. So we have had such data available for 2019, 2020 at this particular point here. You can see how challenging this site is because you have the sea close by, you have ice here actually, you have steep topography, you have a lot of things that change within even 1 kilometer. So it's a challenging site, but it's very interesting to see if we can improve the forecast there. So if we zoom, we see even more how challenging this is. So this Kalman filter, we were able to apply it because we got access to observation data thanks to collaboration with WECAN. And this Kalman filter was written by a colleague. It uses past observation data for training, and it is applied in post-process to improve the wind forecasts. In our case, the GEM 2.5 kilometer forecast that we've been running ourselves with 3-minute outputs. And we are also willing to redo these experiments with a 250 meter resolution output. So just showing some results here that we got. We show here the wind speed in meters per second as a function of forecast time for a particular day in the 125-day period where it was used using an 80-day training. So we see in blue, the model data. We see in black the Kalman filter corrected model data. And we have in red the observation data. So we see that we improve the forecast because the black crosses go closer to the observations. This shows you that we can get an improvement. Of course, I show only one day, but in order to show a bit more what kind of improvement we can get, what we've done here, what we see is the mean of the error square as a function of time for the data, comparing the observation data with the raw model output and the observation data with the output that is corrected with the Kalman filter in the period that we have made the correction on. So the blue curve quantifies the difference between the model output and the observation, and the red curve shows you the difference between it quantifies the difference between the Kalman filter corrected output and the observation. So in other words, I hope I'm not losing you here, but in other words, the lower the curve, the better the result is, because the difference is smaller with the observations. So you can see that in the first 3 hours, pretty much of the forecast, we have an improvement, which is good for wind energy, as we saw, as it was mentioned. So in the short term, it's really good to improve the forecasts. And we are investigating then if we what could happen in the longer term. But as a first result, it's very encouraging, because we see that even for this very challenging site where we are using 2.5 kilometer resolution data as input, we can still get some interesting improvement. And as I said, we'll push that further. We'll try to apply it to 250 millimeter resolution data. But in order to do this, recent observation data are needed. So I think my time is up. I just want to conclude. I've been telling you about this project on icing in RAMS. So on icing, I told you about forecasts that we make at station and on grid using an icing algorithm. We're collaborating with Energica on this case. And as regards RAMP, we are performing 2.5 kilometer resolution forecast on a small grid with high resolution, time resolution outputs. We're collaborating with the University of New Brunswick. We're also performing 250 meter resolution forecast in an experimental mode, which gives us access to more details on the flow. And I told you about the Kalman filter that we are using, and that for which we got a general improvement in the results in the short term. Finally, I told you about how you can access public data using standardized tools, either looking at experimental products using a WMS server, or using the official platform from the MSC called GeoMet, and then data can be visualized on these platforms using different interfaces, or they can also be extracted in a very versatile way using scripts. Thank you very much. Sorry for taking a bit 2 minutes more time, but thanks, and I'll be happy to answer any questions you might have.
Thank you, Simon-Philippe. I think what I'll do is, since we are getting close to the breakout session for the general questions, I will invite the questions for you, Simon-Philippe, to the next session. Matt, if you can work with me to open the session for questions, that would be great.
Yeah, certainly, Chen. I think we've decided to keep, rather than breakout sessions, we're going to just keep everyone together and have a general discussion on forecasting and cold climate. So I mean, I kind of feel like going back to maybe some questions that I've seen in the chat that have remained unanswered, and circle back on some of the presentations. And if anyone has questions, don't hesitate, raise a hand. But just to get the ball rolling, I really like, well, I'd like to hear maybe Charles could answer Eldrick Robello's question about the sort of camera used for the turbine hub, and whether it has a heater, and if you had any problems with freezing rain, snow, and other things in the lens.
Yeah, thanks, Matt, for this. I answered Eldritch in the chat while the other presentation were ongoing, but for everyone's info, Our hub camera, it's a standard IP camera. We use Axis Technologies IP cameras. They're rated for harsh environments, so -40 up to 60 degrees C. They're sealed cameras. They have an integrated heater, and to protect them from the environment on the hub, they're into a stainless steel casing, which is also heated. And so in most icing events, we don't have an issue with ice buildup on those cameras. In some very harsh events, or we have even seen like ice fall basically dropping into the camera, then for a few hours we will have ice over the lens, but then the heater, typically we get back the image within 2 to 3 hours if that happens, but that's, I guess, rare instances. And then yeah, that's the, let's say, external part. And then of course there's a electrical cabinet with communication, power supply, lightning protection, because that's also a concern. If you put something outside a wind turbine, it needs to be lightning proof. So yeah, that's about it for the camera.
All right, thanks, Charles. And you probably answered Phil also, but while I have you here, you mentioned a Japanese OEM.
Yeah, and I don't have the name of the Japanese manufacturer. So we were introduced to the researchers from Japan in the Task 19 kickoff. Brief introduction. I mentioned there was an interest. There's general interest, from communities in Canada, but also from federal entities such as NRCan in understanding what small wind turbines are available for those sites. It's also something Andrea addressed in her speech about the fact that large-scale wind turbines, because their size, but also just because of the amount of energy they produce, is not adapted for the needs of those isolated communities. So there's a general need to kind of find suitable wind turbines that can withstand those conditions. It's also a concern of the Task 41 group, which is addressing distributed wind. Their group is focusing more into making it easier to certify small wind turbines. So that's Task 41 is working on, sub-megawatt wind turbine basically. And a concern that was raised by manufacturers is just the certification from the IEC is very strict on how to get turbines certified. I believe people at WACAN have been certifying small wind turbines, and I believe they could probably comment on this. But it's a challenge for small wind turbines developers to kind of back this whole process, and it limits the options we have on the market.
There's definitely limited options, and any new options that show up are of high interest to everyone, I think.
So that's a long answer to say I don't know the name of the wind turbine manufacturer in Japan, but
when you do find out, share it with us.
Yeah, I will. So
all right, thanks, Charles. I see Ryan's raised a virtual hand. And then there's Rob.
Then we will have another question from Bob Brennan. Ryan first.
All right.
Ryan first.
Am I first? Okay.
Go ahead, Ryan.
So I also had a question for Simon Philippe, and I think there's actually overlap with Brandon's question, so you could probably answer it at the same time. But first of all, thank you very much, Simon Philippe. It's very interesting and a really interesting intersection between forecasting ice accumulation and forecasting wind speeds. And it was a great way to kind of close the formal presentation for this session. So my question is really there's clearly value to making more of these high resolution, both in time and space forecast products available. Can you comment a bit on the level of effort required to make these available at more locations? And what would you see as the next priority in terms of making this available? And this was where the overlap with Rob's question in terms of wind farm operators, utilities and system operators, but there's probably also demand from other stakeholders, potentially transportation and aviation and things like that? It's a pretty open-ended question, but where do you see the level of effort and the priorities in this space?
Hi, Ryan. Thanks for the question. I think it's a very interesting question. Of course, it requires some effort to run, if we were to run grids at several places. That's your question, right? We're interested in doing this. Of course, we need both compute. It uses computing resources, and also there's time to set up everything. But this is something that is feasible, and actually, we're interested. It's very interesting for us to present this today, and we'd like to present it in other instances too. We'll be at the CMOS conference in June, because what we'd like to do too is to know what it's good for us to know what kind of interest there is from the industry in using such forecasts that we are able to make. The question of making them available, as you see, there's some platforms that exist to make data available. As regards running small grids and making all the data available, I'm not sure exactly what kind of resources would be needed as regards informatics and so on. I'm not so familiar with this. Because we've been sharing data with some collaborators, but this was more in some locations and so on. It was not the whole data at all time steps and so on, and higher time resolution as well everywhere. But it's something we could discuss, and we're interested in doing this and in the future. And you had a question about the next step, I think.
Yeah, so I guess that ties, like, would you see maybe making available data on like a per request basis or something like that?
It's something we could discuss. Actually, we're looking at, we have this a project that is financed by Natural Resources Canada, and we're looking into extending. We'll be asking for an extension of the project soon. So this is something we could include, and we could discuss how this could be done in practice. But I think this is something which interests us a lot, and this is feasible. I think. I don't know if Franco had something more to add. I think Franco is in the discussion too. Maybe he has a few words to say on this, more on the practical side of things.
Yes. Hello, Ryan. My name is Franco Petrucci. I work with Simon Philippe at the MSc at Environment Canada. And basically today, the idea was to present the capabilities. So the capabilities for us to run much higher resolution forecasts, to output the forecast at much higher time resolution of, well, we've done 3 minutes, but we could do it even at every time step, which is 1 minute. Of course, the model cannot really discriminate very well between 1 minute or the other, but if you try to fit a curve for the onset of ramps, you get much better time resolution to figure out when your ramp might happen. So this is why we're doing this. And we also presented GeoMet and the infrastructure to give you an idea that instead of putting all those things somewhere where people have to download everything, all the files, and then extract the things, now we have more powerful capabilities where users might just use Python scripts that would query the database and extract exactly what's needed for them. We need to evaluate, the biggest thing here would be to run small windows over areas of wind farms. And this is something that we would have to evaluate how much that would cost. And this is something we want to have a look in the next few months, actually, to have an idea. Okay, if we could run, for example, 20 small windows over many, over most areas of Canada where there are wind farms, how would that be feasible? How much resources would that take in terms of computer infrastructure? And of course, money to run that. And if, of course, users would be interested in that. But from a scientific point of view, and even now a technological point of view, this is now feasible and more easily obtainable from users, instead of us every time providing specifically to a new user information. They could just themselves read the data with a Python script, some Python scripts. We'll develop these a bit more during the next few months.
Sure.
So
thank you, Franco. Before we turn to Charles, Rob Brandon, would you like to do a follow-up question on the utilities and the users viewpoint, or you're okay?
No, I'm pretty much out of this, but I'm very pleased to have seen the MSC's work developed so well. And my question really was, how near would that capability be able to be used by wind farms and utility or more system operators to optimize the operation of the grid system? So no, I don't have a follow-up question. I appreciated the response.
Okay. Thank you.
All right. Are there any other questions?
I think Charles has one.
I wanted to follow up on the discussion because I also found it very interesting, the MSC work, Simon Philippe, and I kind of also wanted to comment on Rob's question about the interest from operators. So as you've seen in Simon Philippe presentation, we've been doing some kind of validation work at first at our site, where as an operator, because we also have a wind farm there, we do have interest for that, for sure. But we also have a project where we're using those forecasts for operating the icing system preventively. So with those forecasts, we're actually sending alerts to an operator for several wind farms across Ontario, Quebec, and Nova Scotia. And there's definitely interest in them knowing the severity of the icing that will hit, and also the duration of that icing event. So that's part of the work we've done on top of what Simon Philippe presented. And I can vouch for having been supervising work of people just building script to unwrap tar.gz archives that this MSC platform is very interesting. I think it's a great tool. I like the mapping as well. And Simon Philippe, I had maybe a question about the timeline, because you mentioned you wanted what's available now and what's coming up next. It was unclear to me, like what's already available through the platforms you showed, and you also talked about the scripts. So those two things, when are they available?
What is available now? What I told you about GeoMet, as far as I understand, everything from the operational models that are run at the CMC, whether it be probabilistic models, regional, national, global, my understanding is that you can access everything using GeoMet right now, using scripts. And on the web page I showed you, I didn't have time to mention it, but there's examples of scripts already. For example, there's a script of there's a man called Arthur who has an umbrella shop, and he wants to find out, to estimate how many umbrellas he would sell on a given week, according to how many possibilities of precipitations are forecast by one of the models. So it's very interesting. You can just copy paste the script, try it for yourself. So it's very interesting. So this is from the operational model outputs, but as I said, sometimes it's limited. I mean, for example, the HRDPS, it outputs data every 30 minutes for the first 24 hours, and then it's every hour. And then with this suite we're running at the MSC, we're sending Energica data every half hour from the HRDPS, for example, for the first 24 hours. But as of now, GeoMet gives access to hourly data. So it is, but I've heard there's discussions to make it available at a higher resolution. But for now, this is the way it is. So you don't have access to everything. Let's say probably not all the output variables either. I would have to check that. It's you can check on the website. For example, I think the very fine the specific variables regarding icing, for example, liquid water content and these things, I'm not sure that they're available publicly right now. So this is for GeoMet, and then for this WMS server, there's a lot of experimental products there. So for example, on this, using this suite I showed you, we send some icing forecasts on maps. But there's also other models at this SMC, which are, I don't know if you know, I didn't know before working at the MSc, but you have some what is called operational models. So these are the models that have been going through a process where it's accepted by a committee. So it's like you get a stamp that this model is operational, and then the forecast can be made available, and you know that the models have been checked and so on through different processes. And you also you have also experimental models, which haven't gone yet to this process, but there's been some verifications done and so on, and you have a lot of data available there too. So it's like it is a step before getting operational for many of these models. So if you go on the Meteo Sound Plus website, you can see all this list of models, all the fields that are available as of now, and I think it's changing. Sometimes there's some additions to it, and so I think it does it answer your question? Yes.
Yeah, sure. Thanks. That's very interesting, and for sure something we'll probably end up asking you a few questions on those Python scripts.
I'd be glad to try to help you out with this.
Thanks.
And Phil used to have his hand raised. I don't know whether he still has a question or not.
I guess more of a comment than a question, just very interested in this conversation, very interested in the application of it as well. I see this point that we're at where, well, I guess it was Taylor mentioning 2 days ago about the wind discount in Alberta bidding in at $0, which makes for a wind must run kind of scenario. But as we push into higher levels of wind and solar on the grid, that forecast just becomes more and more critical as to how much can I play into the market in the day ahead, or if it's a vertically integrated utility, how much can I depend on that resource in the day ahead, hours ahead, and that kind of thing. And so that bridge from what you're doing right now to the actual application, the use of it day to day in the markets, I think is really interesting. Would you be interested also to see accuracy, and I apologize if you did this, I had to step out for a few minutes, but against what AWS True Power is doing? I think they're under UL now, but that they do a lot of the forecasts for the North American wind business, and so I think it's like 60% of the continent's work or something. So that's kind of the target to beat, and if you can demonstrate that that's better than what they're predicting, more accurate, that's the benchmark right now. I think that's worth pursuing. So very exciting work.
Thanks for the comments. Very interesting. I'll have a I'll have a look at what the UL is doing. I know people working there, but it's interesting. One thing I wanted to mention is that as for verification, we willing to work further with this, but we need the problem is always to get access to observation data to make comparisons. So we're working on getting access to such data too, to be able to make comparisons and verifications. But I know that, as Charles mentioned, Energica has been doing some verification, for example, for the icing part. And I think the University of New Brunswick as well is checking some of the forecasts that we send them. So I don't know if they have something to say on that, Charles. For example, I would be curious to know lately how the icing forecasts have performed. We haven't talked for a while, so I don't know if you would have something to say about this.
Yeah. So we're very much looking at icing at our site. So we have a lot of instrumentation looking at it. And what we've seen is that for like severe icing events that are, from complex or like large systems, typically those we can predict well. Then for smaller events, so from the models, we have a lot of the big events we do see. However, we tend to kind of over predict icing with the model typically. So a lot of like small icing events are predicted and they don't really occur. but that's kind of they have less impact on our production, I should say. And then there's the timing, which is, can be just a few hours. There can be a little delay between the prediction and what's actually happening, but it's in general for like significant event caused by a large meteorological system, it's quite promising. Yes.
In terms of the power production forecast in comparison with AWS true power, we did the comparison using, at that time, Simon Philip, we were using the data for 1 hour resolution, 2.5 1 hour, not the high resolution. But probably Bo, if you can briefly comment on the results of comparison for hourly forecast and day ahead forecast. I think that would be Phil Mackay's.
Yeah, actually, it's that we collect the AWS true powers forecasting data for more than 4 years, and we did very comprehensive comparisons between the AWS true powers and the Environment Canada's models. What we compare that is particularly in wind speed forecast. They had wind power production forecast, and ours had wind power production forecast. So it's very comparable. So I think even the UNB models based on the input of Environment Canada's model, the wind speed forecast, even we have compared in terms of the performance, even slightly better than AWS true power. And also, like I know the Simon Phillips send us the 3 minutes, the high resolution data for I think more than 2 years. We compare that. The 3 minutes data is not. There's not a significant improved one we used for short-term wind power production forecast, but it's definitely improved the ramp event forecasting a lot, because the higher time resolutions for sure to include more and more information of wind variations that will help the ramp event forecast. That's it's a basic picture. But from wind farms operator and system operators perspectives, the public the wind forecasting based on this public model is valuable, but the main challenge we found is the maintenance and how we could send our forecast for the wind farms operators or utilities. They try to have these forecasts in an easier way. That's the challenge part. How we can provide we can provide accurate forecast, but how we can provide them in an easier way, that's a challenge for us.
Thanks, Bo. Lucien, I don't know if you want to continue on the forecast subject, but
I think probably it's about time, Matt, to switch to icing.
Well, I was going to kind of change the topic a little bit, but I actually had a question for Andrea, because I've been wanting to ask this question since your presentation. Andrea mentioned, I thought it was very interesting, the idea of offshore wind being potentially more, how did you put it, more structurally sound, I guess, or reliable, but for those who probably maybe don't have access to or that aren't coastal communities, I wasn't quite sure whether bigger hub heights were better, for specifically related to the topic that you were referring to.
Yeah. So oftentimes with remote communities, getting the equipment to the site is the limiting factor. That's the bottleneck. If it is an island, if it is inland and geographically isolated, it is the issue of what will be determined as to how can you get there? How big are the roads? How stable, how strong are the bridges? What can we bring to this site? So I guess it's a balance of, what is the opportunity cost? What's the cost benefit analysis? There's a whole economics side to it. But I think part of it is the reality that if we are in the best case scenario, going to put the best onshore wind turbine on a site, what are the added costs that we have to consider given the instability of the ground? And if a 37-meter hub height wind turbine had that kind of cracking around it, can you imagine what could happen with something larger and the impact that would have? And some of the subtle things that we forget sometimes to consider is that any sort of vibration will have a thermal impact. So as soon as we have resonance and frequency between the tower to the operation of the turbine, and then we add on, of course, the icing issues, not only can it be difficult to operate, it's just in a perfect situation, but when your ground isn't stable, it's a whole other reality that we have to consider. So yeah, and I work a lot with these remote communities up north and in the Arctic, and the question has always been, okay, what does the energy transition look like? But I keep coming back to, can we even do an energy transition given the circumstances, the reality that we're facing? So it's something I'm struggling with, I don't know, just coming to terms with the reality of what that could potentially look like in this environment. So yeah, and that's why offshore might actually be a little bit more predictable, even with sea level rising, right? And the technology moving to floating bases and things like this. But yeah,
there's a lot of moving parts for integrating renewables in the north. That's for sure.
Yes. Thanks for your question.
Thanks for your answer.
Actually, if we can have a follow-up question for Andrea, to you too. You presented the cost analysis, and it seems wind energy or renewable in general can provide a cost-effective power generation for remote communities. Yet, are there any projects currently ongoing in these remote communities for wind or solar?
Did you say projects? Was that
projects or production?
Yeah, so there are some, and there are a lot of smaller microgrids up in Alaska, remote Alaska, some in Canada, but we still are seeing those diesel hybrid systems, wind and diesel, but we need to move to this transition. And that's what my research really focuses on is that smart, intelligent microgrid design for these remote communities and climates that are quite harsh. And when I guess the economical part of it is that when you change diesel out, you're going to find the most savings because that is so costly in these communities. So renewables become favorable, but it's not as impactful as if they were synchronized properly through optimization and proper management of the microgrid. So when we have this intelligent distributed generation, that's where we really see the differences. That's where we can make huge changes. And that's where we've seen some 90% price drops at certain times of the day. Of course, we're still working to get to 100% renewable. It's very difficult in some places, especially given the limitations. Some places won't have biomass, for example, but you can't just rely on one or two of the renewables. You also, of course, need storage. You have to diversify storage, you have to diversify generation. And when you synchronize it properly, that's where the savings are really found. And that's in most places, but it's going to be most significant in our remote communities, especially isolated ones, if we can get there. And the scale can be smaller too, because of the demands are smaller in remote communities. So then we can size it more appropriately.
I'm just wondering if I can jump in on this. I think, Andrea, what you said is very interesting. And I'm wondering about, we've seen some issues in northern communities with very small load. And so therefore the wind turbines, they're just not available, as we've heard on this in this session. There's just not a lot of small wind. And so this idea of sector coupling in the north that deals with probably an intersection of issues, whether that's water supply, whether that's heating, transportation. And so to the extent that sector coupling can help both increase the load to allow a broader range of technologies, broader range of wind turbine sizes, brings an economy of scale there as well. But then I guess there's this balance against what you said around how big is too big up there, and that creates issues as well. Have you thought about that side of things?
In terms of the coupling part, or
in terms of the coupling, and how that might come into play.
Absolutely. So when we look at this, and we start to look at this, really extends into my work into the circular economy. When we start to see energy systems and what they bring in, we are now also bringing in e-mobility distribution and throwing that through all the way to the waste. So if we can start making our putting our waste back into our energy economy, we are going to start closing the gap on some things, so we can then resize appropriately. So then, how big is too big? That's really it. It's about sustainability, right? It's about how do we deploy these systems so that we're not overproducing, because that's costly. We're not over storing, because that's costly, and really optimizing that size so that they make sense in some of these communities, not only remotely, but I think it extends to smart cities and where we're going in the future energy economy.
Yeah, so, absolutely. Yeah, there's a sweet spot there. Good, thanks.
Yeah, you're welcome.
Will you be attending renewables in remote communities in Yukon at the end of the month?
Oh, I wish. Send me more information. I don't know if I can make it happen so fast, but I would love to be there. Even is it virtual? I can be there virtually.
I think there is a virtual, yes.
That'd probably be easier for me to get to. Yeah.
I'm trying to convince my bosses to go to. I think we've probably run out of time. Marianne, is that? And I think there's already been a couple people dropping out, but I'd like to extend a thanks to everyone who presented, everyone who asked questions, and everyone else who was attending. Thanks to Marianne for organizing this, and WCAN and the whole committee.
Thanks, Matt. Thanks, Lucien, for moderating today. And I'll second Matt. Thank you for all of the great presentations and the wonderful discussion. Join us Monday for offshore wind and social and environmental integration. Have a nice weekend, everyone.
Thank you.
Great.
Thank you very much.
Thank you, everyone. Have a good weekend.
Thanks, everyone. Bye.
Bye.
Bye.